Those who have not, those who did not get the tutorials, please open the first tab in the A view and right click on the tutorial. So if I say, is the screen being shared with them now? They are able to see. Okay. So maybe you should show them how to get into that and get into the option. No, but probably they did not see how you opened the tutorial tab. So I go back here, I go to the first tab. Where is the library tab? Okay, so can you just say this to them because they don't, because I've been trying to.
Yeah, you can find their name, library. Yeah, the top one. That is the user name. I'll show you there.
You have to show them.
That is the user name. I'll show it there.
Okay.
Just explain them accordingly.
Okay. There's a download document. So you have the tutorial right in front of you. You right click, you will see download document, and then you save it in your desktop or where you're running this software from, and then please make sure that it reaches all the students. All right. So because it's very important to do this screen area. It's important to do these tutorials because otherwise it's you have no way of testing whether you understood the concepts or not. And after you finish doing the tutorial, I'll send you the solutions so that then you can verify. Just having the solutions right in front, try that out first. And when I say that, you know, ask whether there are any. They got it. UIET got it, but the student seems to say that they do not have it. Now how do I get back the desktop sharing? No, I wanted to see the class. So next time, so the UIET teacher representative, can you please raise your hand? Okay, please make sure that the students get the tutorials and the students work on them. Otherwise, as I said, there is no way of checking whether you understood the concepts taught. This is only the first tutorial which contains the content corresponding to the first part of the transmission line. We're going to be doing, I'm going to be sending you the next tutorial soon, but I wanted to make sure that whether you have solved the first tutorial, whether there are any difficulties. If yes, this is the forum to address them, and then we can go ahead. This just becomes a meaningless exercise if you are also not working along with the class, I mean the content. Yeah, so every college can download that. Please download that if you have not done yet, and next Tuesday's class, please come up with questions if you have any. By next Tuesday, we would also, next Tuesday I'll also upload the second tutorial, so that next Thursday, please come up with difficulties. Please use this forum to discuss the difficulties in tutorials. I can always give you a solution, but that will be the solution that I have written, right? So if you want to understand, it is not just enough having the solutions right in front of you. You need to solve, and then when you solve, you start thinking, and that is when you start probably getting some questions. That is when you are checking your understanding. So it's very important to do these tutorials along with the class. All right. Okay. So today's class, what we are going to do is, as I said last time, we did the concept of transmission lines, and we discussed that we actually said we did not use any electromagnetic field theory. We just did circuit theory because that is very familiar to us. And even with circuit theory, we said we were able to understand that there is a delay between the voltage that is emanating from the source and what is appearing at the load, and we try to model that, and we try to also see that because of those delays, or rather these delays are due to the waves, the voltage waves and the current waves that are set up in the line. And these voltage waves and current waves, it is not only in one direction, the impedance is not matched, you have reflections, with the result that you have standing waves in the electromagnetic, standing waves in the transmission line. And the consequence of having those standing waves we discussed in detail. What is the impedance match? Finally, because of all that, you have some power reflected back, you have some impedance mismatch issues. We also discussed how to get rid of those issues purely with the perspective of circuit theory, without knowing anything in what is an electromagnetic field, without knowing what is electric field, magnetic field, flux, etc. That's good way of doing it for engineers who probably can, equate everything in terms of circuit elements or in terms of impedances. This is good. But there are two fundamental issues there which we kind of hid under the carpet. The fundamental issues are, when we did transmission line in the beginning, you talked about voltage wave and current waves. We wrote down we of course wrote down the differential equations which verified that the voltage and current are actually waves, right, traveling waves. Right. So this we did from first principles. We did not have any assumptions there. We just assumed that there is a delay. The delay was modeled as a resistor and a capacitor, and then we said this voltage and the current in this setup is propagating as waves. But suddenly somewhere we said the wave velocity is c, without any reason. We did not give any reason, at least we did not discuss why the wave velocity should be c or even related to c, the velocity of light, right. That's something we just said, the voltage will travel with it c or related to c, it is c by 2 or 3c by 4 or so on. The other thing which we hid under the carpet was, we did not say how to find RLGC, the resistance per unit length. How do you actually calculate that? Yesterday, of course, in yesterday's class, how we said, I told you a method how to calculate the ZO by doing an open circuit and a short circuit measurement. I said ZO is simply ZO open circuit, ZO Z short circuit. Proved that. But that, I said, remember, that was a quick way of measuring. If I have a line with me, somebody is giving me a transmission line like this to know what is the impedance. how does an engineer quickly find out what is the effective impedance or the characteristic impedance of the line? Do a short circuit measurement, do an open circuit measurement. That is a quick way of doing it. But suppose I want to do an inverse problem, in the sense I want to make a line of a particular characteristic impedance for impedance matching or for a desired characteristic impedance. I want to make that line, which means I want to know what metal to use, what should be the spacing between the two outer conductor and the inner conductor, whether it should be outer conductor, inner conductor. Why can't, so I can have two parallel lines, or I can have an inner conductor and an outer conductor kind of a coaxial cable, or I can have, if it's on a substrate, I can have the top plate and the bottom plate of the substrate. I could have microstrip lines, right? How do I design those? I need to be able to find a way to find out the more importantly inductance, capacitance, and of course resistance and conductance. Now these two, if you want to get little deeper into the design of the transmission line, this pertains to the design of the transmission line. You have no choice but to do electromagnetic fields, right? You want to be knowing about electric field, magnetic field, electric density, H, all these, current density, charge density. You want to be knowing about all these, you want to be knowing about all the rules that govern the flow of energy through the transmission line before you could find answer to these questions. Now where is electromagnetic field coming in here suddenly? All what we were talking about is an inner conductor and an outer conductor. The inner conductor, outer conductor connected to the source, and at the other end that is connected to the load. Looks to me as an electric circuit. Now where is field coming here, sir? What is the connection there? The connection is the following. As I said the other day, if you think about it, you have, so if I look at the cross section of the coaxial line, this is the inner conductor, this is the outer conductor, and you have a dielectric. This material is a non-conductor, it's a dielectric. Let's say for an instant of time the inner conductor is positive, the outer conductor is negative. It means there is a potential difference between the inner and the outer conductor. There is an electric field between the inner and outer conductor. So for that, let us say this is the direction of the field. So that is about the electric field. And if I just look at the inner conductor, this is now a current conductor. Now a current carrying conductor would always have a magnetic field associated with it, right? So that magnetic field in this, so if this is my inner conductor, that magnetic field is your high school, that is, so if this is the conductor which carries current, the field is given by the direction of my fingers. It's curling around, it's rotating around, it's circulating around the current carrying conductor. So there is a magnetic field, there is an electric field in this. So what you have set up there is a pure electromagnetic problem. Even though all the 6 classes or 7 classes until now, we never talked about electric and magnetic field. We were talking in terms of voltages and current, but these voltages and currents are nothing but manifestations of electric field and the magnetic field. Voltage is in a way analogous to or represents the electric field, and the current is representing the magnetic field. Now, yesterday we worked out what is the power direction of power flow and how much power is transferred from the source to detector and so on. What is the analogous quantity here? So you have, let us say this pen is representing my inner conductor. I have a magnetic field around it. I have an electric field. So electric field is, let's say, radiating outward. Magnetic field is curling around all along the length of the conductor. So the electric field and the magnetic field at any point on the line are coexisting. They are coexisting. And so what you have set up is an electromagnetic field there. And what is carrying the energy forward? It is the electromagnetic field that carries energy along the length of the line. Alright. So you have an electric field because the two conductors are not at the same potential. You have a magnetic field because the conductors are carrying current, and so you have set up an electromagnetic field, and it is this electromagnetic field that is carrying energy. Now, there are many questions here. How do I know what is the energy carried by the electric field and magnetic field? How do I know that the direction of the energy is along the direction of the conductor? I can't intuitively say, or you can intuitively agree to the fact that magnetic field is along circulating, electric field is radially outward. What makes, or what, how do I know whether the energy carried by the electric field, or what is the energy carried by electric field, how much is the energy carried by the magnetic field, how much is the energy carried by the electromagnetic field? There is a wave coming from now. Where is the wave corresponding to electric field or magnetic field coming from? What is the nature of that wave? Would that change when the medium changes? How does that information help me to calculate L and G? These are the questions that we have now. And to be able to answer these questions, you need to know the fundamental, your Maxwell's equations. Right, the four Maxwell's equations, which are the four pillars of the electromagnetic field theory. But to be able to understand Maxwell's equations, I am not going to write them down here. We will try and start from first principles. To be able to know what the Maxwell's equations are, or to appreciate the meaning of the Maxwell's equations, you need to be knowing some basic information on vector calculus. Some terms, some operations we will be continuously referring to. So you need to be having some idea about what those operations are. Mind you, this is not a class for vector calculus. So I would be only referring to them in the context of our application. So I am not going to be doing the entire vector calculus for you. I am not going to be doing the entire coordinate geometry and transformation of coordinates and all, because we have only maybe around 7 classes now. So what the plan is to do introduce some vector calculus today, so that when we write down Maxwell's equations in tomorrow's class or the next week's class, we will be able to appreciate what's the meaning of those equations. And by the end of this lecture series, we will get back to the answer to this question. We will go back and calculate using Maxwell's equations. We will go back and calculate RLGC for a transmission line. We will go back and calculate what is the wave velocity in the transmission line, so that the loop is complete. Right? So that's the idea. Again, the screen has. So what we want to be some totally dissociated content today, which is some introduction to some vector notations which we will use. So you know what a scalar and a vector is. You know that the physical quantity is represented only by magnitude. It's completely described only by magnitude. It's a scalar. If the physical quantity requires a magnitude and direction for its representation, you call it as a vector. Examples being, for example, temperature. It's a scalar quantity. I don't have to say 32 degrees in which direction. Vector, for example, velocity. Want to be saying the velocity is the velocity of my car is 60 kilometer per hour, but in which direction, right? These are some things that you already know. Now, if I have, so we will be talking about scalar fields and vector fields, right? We will be talking about scalar quantities and vector quantities. Let's talk about what a line integral is. For the class, have you heard about line integral? Yes, please raise your hands. Okay, so we'll quickly refresh what you know in the context of the requirement of the field. So let's say I have a vector field which is pointing in this direction. This is my vector field. Okay. Now I want to know what is the effect of field, or I want to calculate some effect of this field along a line which is running from A to B. Typical example where we would use is if this is an electric field, if this represents, the lines represent an electric field, let's say I want to know how much work I need to do to take a charge from the point A to the point B. Right, that's a context where this line integral is going to get used. Then the line integral L is dot dl. dl is an elemental length so dl is elemental length along that line. This is, if I were to calculate from A to B, all what I need to do is to find, this is my vector field A, I need to find the tangential component of the vector along dl, the component of the vector along dl. So if theta is the angle, then the component of this vector along dl is going to be A cos theta, magnitude A cos theta, because I will calculate what is the magnitude at that point. Cos theta times dl. I keep doing that all along the length and keep adding all that. That would give me the total line integral. So to calculate the line integral, what I need to be doing is, if I want to calculate the line integral from A to B, I'll have to divide this A to B into small strips, each of length dl. At every strip, I would see where is the direction of my vector A, calculate the component of that A along that line, and then add it up. So in a way, that is kind of giving you an effect of that vector along the line that I am considering. For example, I could have the same vector field, I could have my line running like this, my contour could be this, or my contour could be something here in green. What at that point, if you see, this is theta here for this length, this is theta, for this length, this is theta, it's changing, right? So if I keep doing this, so if I and add it up, this is going to be my line integral, which can be represented like this. So in the I mean later on we can work out an example to find the line integral. Just trying to look for a help you find the line integral. We can do that very quickly here. Let's say for convenience, this is y, this is x. My vector field is along this direction, right? I have a vector field which is A is some A naught in the AX direction, uniform vector along the AX direction. And let's say I want to calculate the line integral here along this line. Can you guess what this is going to be? Now this line, let's say it's running from y1 to y2. Now I want to calculate what is from y1 to y2, or A dot dl, right? Y1 could be any number, y2 could be any number. You can immediately see that intuitively itself you can say that the angle made by this line with the vector is 90 degree, which means the tangential component is 0. So I can immediately say for this case the line integral is 0. Alright. Instead of I can write it out also explicitly and say that this is A naught AX direction dot, what is the direction of dl? Dl is the elemental length and that is along y. So you will call that as, let's call that as dy ay, because this is my dl now, the direction of the elemental length, because I want to calculate along that direction. And ax dot ay dot product is 0, we know, so my answer is 0. Alright. Now suppose I want to calculate the line integral along, for example, this line, which is running from, let's say, x1 to x2. What would this be? In this case I would have x1 to x2 A naught AX dot. Now you see the elemental length is pointing. Now I want to find the line integral along the line which is running from x1 to x2 in the x direction plus x direction. So this is going to be Ex Ax. And in this case, because A naught is a constant, it's a uniform vector field. What is the meaning of uniform vector field? At every point the magnitude of this is constant. It's not changing as a function of x. I could have vector fields where instead of this I could have x Ax, which means as x is increasing the value of the field is also increasing. I could have vector fields like that, but I don't have such a field. I have uniform field. So this is A naught Ax dot Ax is 1, so it's simply x1 to x dx, which is A naught x2 minus x1. I get a number at that. But in case the vector field was non-uniform, I have to appropriately integrate. Now similarly you can extend it to any contour. For example, if I needed to find the along this, well, let me try to choose another color here. Let me say I want to find it across this contour. What should I do here? I will have to represent this dl now. So let's say I want to find from this point to this point. So this is my dl. What should I do in this case? I should say my dl, I'll have to find out what is the component of this dl along the ax direction, component of this dl along the ay direction, and then use it, well, use it here. So I'll have my answer as two separate integrals, because I'll have an x component and a y component. X component along with x component will give me, with x component will be a result, whereas this would give me 0. So this is how I go about finding line integrals. What is it telling you? It is actually telling you physically what is it? It is telling you the projection of this. It's telling you the projection of this vector field or the effect of this vector field along the line that I am considering. So I have, let us say, the fingers are representing my direction of the vector field. If my line is here, it actually tells me the projection of this field along this line, the effect of the field along the line that I am considering. That is what line integral is telling you. All right. Now we move on to surface integral. So again, let's say I have a vector field, and let's say that, so again let my fingers represent the vector field, and let's say this vector field is cutting this surface which is my palm, right. So the vector field is at this angle, that is cutting a surface, and the palm, my hand, the palm of my hand is that surface, right. So I'm trying to draw that here, something like this. This is my surface. Remember, this is necessary that the vector field and surface are normal to each other. This could be like this, vector field could be this at an angle. Now, so if I have a continuous surface, smooth surface, the surface integral, which is also called as the flux of vector A, remember this term flux, it will keep appearing in electromagnetics. Flux of A through the surface S is, call it as psi, call it as surface integral. Some books show this either as one integral or it shows as two integrals to show that it's a surface integral. You again do A cos theta ds. In other words, what you are actually doing is surface integral A dot ds surface integral A dot ds. Now I have marked ds as a vector. Now what is this ds and what is the direction of that vector? So if this is my surface, every surface at the point at which you are calculating, it will have a normal, a surface normal. If my surface is like this, the surface normal is like this. If my surface is like this, or if my ds is like this, the surface normal is this, outward normal. If my surface is this, this is my surface normal, right? Which means if I am doing this integration, I have to do this integration just like in line integral. I have to do this integration, I have to imagine that the surface is made up of many small surface areas, smaller surface areas, and at every small surface area I calculate what is, or I find out what is the outward normal AN, right, outward normal AN, and ds, magnitude of this ds times outward normal, or the magnitude of the small area ds when multiplied by, or when it is getting a direction of ds is nothing but outward normal. Magnitude of ds is the magnitude of the small area. Alright. So you take the dot product of the vector at this point. So the vector is this. So take the dot product of this vector with its magnitude and direction, dot it with the ds which has a magnitude small ds or d this magnitude, and its direction is the direction of the outward normal. Keep doing that for the whole surface, that will give you the surface integral. Alright. You can extend it to the third dimension. So first you talked about line, then you talked about surface. What is the meaning, what is the physical meaning it is conveying? It is telling you how much total field is, what is the effective field that is crossing that surface. So if I have this field in this direction, I have the surface here, what it tells me is that how much of this field, the surface is at an angle, how much is the effective field that is crossing the surface, the component of the field along the direction of the surface. Same kind of examples you can work out, but now you have ds means you will have in two directions, two dimensions. So if I have, field is in this direction and the area is perpendicular to this, you can imagine that. So what would it be? So let's say I have the field in this direction and my area is in this direction. The area that I am talking about is in this direction, vertical, which means my surface normal is along, AN is along the direction of my field. My flux is maximum because the cos theta component is AN and vector A are in the same direction. So the flux is maximum. Flux crossing this surface is large. Whereas if you compare it with this case where this is my area field, and let's say the area that I am talking about is in the horizontal plane. Area is this, the field is this. The field is pointing, let's say, towards you. I am talking about an area which is parallel. Clearly, in this case, the surface normal is here and the field is in this direction, angle is 90, so your flux is going to be 0. So what is flux telling you? Flux is telling you how much of the field is actually cutting the surface, how much of the field is crossing the surface. Effective field is crossing that surface. Alright. So in this case your flux is maximum, in this case your flux is 0. Flux is again quantity which we will keep saying when you talk about the Maxwell's equation. In fact, the first Maxwell's equation talks about the flux. Now similarly you can extend it in the third dimension and talk about volume integral. Volume integral, not going to go into detail, you can extend the whole thing in the third dimension, it's rho dV. Now the next concept that we want to know about is, after talking about line integral, surface integral and volume integral, the next thing what we want to talk about is gradient. Of a scalar field. Okay. Now think about a physical situation. Physical situation, for example, say the surface of the earth, and you know that I'm talking about a scalar. So the first example I gave you for a scalar field was temperature. So I know that temperature is a function of z, where z is the, the height, distance from the surface of the earth. Considering an example there. Now I want to know only on z in this case, okay? It changes only as a function of height. It is not changing as a function of x and y. Now I want to know what is the temperature at this point. I know what is the temperature at height 1. How would I calculate the temperature at height 2? I can do that provided I know what is the temperature gradient. Temperature gradient is nothing but rate of change of temperature with height. If I know that the temperature is changing, for example, I could be totally wrong in this case, but let's say for a number, let's say there is a 1 degree change in temperature, 1 degree change in temperature for every meter. That is my temperature gradient. So if I know what is the temperature on the surface and I know that it is changing at a rate of 1 degree for each meter, I know that at 40 meters it is going to be 40 degree more. If for lower temperatures, for lower heights, the temperature actually increases up to a certain point, and then beyond that it actually decreases. So if I know, I need to know the sign also, whether it is increasing or decreasing. Let's say we are talking about higher temperatures, higher heights, altitudes, where the temperature is falling as a function of height. So then I'll have to say that this is minus 1 degree Celsius per meter. Simply means that if I go from 1000 meters to 1100 meters, I am expecting a drop of 100 degrees Celsius. So that is where, that's the meaning of gradient. Okay, so that is the meaning of gradient. Simple enough to understand if temperature is varying only as a function of z. But let us say I am sitting in the studio where the temperature is not varying as a function of z, but I have variations as a function of x and y and z. For example, I have the vent of the AC right in front there, so the temperature there is going to be lower. I have some instruments, amplifiers, some things kept here which is emitting heat, which means the temperature there is going to be higher. So if I measure the temperature at each and every point in this room, I actually have a distribution which is a function of x, y and z. At every x, y, z location, I have a different temperature. Then how do I talk about the concept of gradient? If it was in one direction, I know that the gradient in that direction. But now I am talking about a variable which is temperature. It's a scalar variable. It's a scalar, but it is a variable because it is changing as a function of position. How do I find the gradient for this now? Essentially my question is, if I know what is the temperature here, how do I, or in this room, if I know what is the temperature at this point, how do I find the temperature at this point? Yeah. So knowing this T1, how to find T2? If it was depending only on one direction, or the temperature was a variable depending on, temperature was a scalar variable with only z dependence, I just multiply that. But what if it's it dependent on all three directions? That case, what is helping you is to get actually the gradient, to define the gradient of the field, and the gradient in this case is del t, where del is the operator I del by del x or ax del by del x plus ay del by del y, az del by del z of the scalar t. This is what I would have. Now why this happens, maybe we can discuss in the next class. Why is gradient this function, we can discuss in next class. But remember the answer you get, now remember this t is a function of x, y, z. The answer is a vector. So the gradient of the scalar is a vector, which means the gradient, the change, is depending on the direction. It's intuitive to understand that. Because temperature is varying as a function of space, if I want to know what is the change, you have to tell me in which direction. The direction of change in temperature, if I go in this direction, the change is different. If I go in this direction, the change is different. If I go in this direction, the change is different. You have different changes in each direction, which means the gradient has to be a vector. You have to find out. So if I want to find out the temperature at this point, at the third point, what you need to be calculating is your directional derivative. So what we wrote down here is dt by dz, which is not directional, but what we should be doing in, if t is a function of all three variables, what you should be, it is not simple derivative, it should be a directional derivative. So in tomorrow's class, we will talk about how to find directional derivative, why this gradient turns out to be this number, and then we go on to curl and divergence and curl, then to Maxwell's equations. We stop the class now because we are indicating that the time is up. Open the class for questions now. Just to summarize, what we did today is I told you what was a missing part in transmission line, which I said the velocity of the wave and how to calculate the RLGC components values. And I said that to be able to do that, you have to understand the concept of electric field and magnetic field inside the transmission line. To be able to understand that, you need to do the Maxwell's equations. To be able to appreciate Maxwell's equation, you need to understand some vector calculus. We started off with vector calculus. Hopefully by the next class we will complete that and get on to Maxwell's equations. Questions please. If there are any questions, please hand raise. Please raise your question. Oh, there is a question. Okay, electric field and magnetic field exist simultaneously. I will answer that question in the next class because we will talk about the simultaneous coexistence of electric field and magnetic field. Also realize through Maxwell's equations that how they coexist. So they do not interfere, they coexist. And together the electric field and magnetic field, if both of them are propagating or if both of them are time varying, the result is an electromagnetic wave. So that we will talk about in detail when we deal with Maxwell's equations. Any other questions? Either type it out in your question tab or hand raise.
She is giving to us only one question. She is doing something. You are an actress in one of.
Okay, so if there are no more questions now, we stop the class. If there are questions further, please send it as an email to the QEEE.